Αγαπητές φοιτήτριες και αγαπητοί φοιτητές, κύριε Πρίτανη, κύριε Αντιπριτάνης, πρόεδροι των σχολών, τμήματων, κοσμήτορες, κύριοι καθηγητές, κυρίες και κύριοι, είμαι ο Παντελής Αβίδης, πρόεδρος του Συλλόγου Αποφοίτων του Αριστοτελείου Πανεπιστημίου Θεσσαλονίκης και οι συνδιοργανωτές μου έκαναν την εξαιρετική τιμή να συντονίσω τη σημερινή εκδήλωση. Να απευθύνω ένα χαιρετισμό για την παρουσία ενός του εκλεκτού μας προσκεκλημένου, του κυρίου Κίπ Θόρν, ο οποίος είναι ένας από τους πλέον σημαντικούς επιστήμονες εν ζωή διεθνώς και από ό,τι αποδείχθηκε και από την ταινία Interstellar, αλλά και τις ρυθμίσεις που έκανε εδώ και εξαιρετικός σκηνοθέτης μάλλον. Είναι μια εκδήλωση που περιποιεί εξαιρετική τιμή για την πόλη, αλλά και το Πανεπιστήμιο. Και ευχαριστούμε τις εκδόσεις Ροπή και προσωπικά τον κύριο Πάνο Χαρίτο που τις διευθύνει, ο οποίος φρόντισε να βρίσκεται μεταξύ μας σήμερα ο κύριος Κίπ Θόρν και να απολαύσουμε την ομιλία που προβλέπετε ότι θα είναι πάρα πολύ ενδιαφέρουσα. Είναι ένα ταξίδι, κυρίες και κύριοι, αυτό που θα παρακολουθήσουμε σε άγνωστους και δυσνόητους κόσμους, αλλά πιστεύω πως θα το κατανοήσουμε χάρη στην εξαιρετική διδακτική δυνότητα, όπως σας είπα, ενός από τους σπουδαιότερους εν ζωή επιστήμονες, του καθηγητή Κίπ Θόρν, και για όσους έχουν διαβάσει το βιβλίο Interstellar, του καθηγητή Μπραντ, αν δεν κάνω λάθος. Το βιβλίο που έχει γράψει είναι ένα εξαιρετικό βιβλίο, είναι ένα εκπληκτικό έργο που έχει μεταφραστεί στα ελληνικά από τις εκδόσεις Ροπή. Δεν υπάρχει περίπτωση, ακόμη κι αν κάποιος δεν έχει ιδέα από φυσική, να μην καταλάβει λεπτές έννοιες, αλλά που έχουν γίνει καθημερινότητά μας. Ένας τρομερός συνδυασμός εκλαΐκευσης, αλλά και επιστήμης. Αυτού του είδους τα έργα, αλλά και οι μεταφράσεις, είναι προσφορές, κυρίες και κύριοι, δεν είναι επάγγελμα. Ουσιαστικά το βιβλίο είναι μια ερμηνεία της ταινίας, η οποία κινείται σε καθιερωμένες επιστημονικές γνώσεις, εμπεριστατωμένες υποθέσεις, αλλά και εικασίες. Όταν είδα την ταινία, και επειδή λόγω ίσως και ηλικίας μου αρέσουν οι ταινίες να έχουν ένα happy end, είχα μια αίσθηση ότι το κοριτσάκι, η κόρη του Κούπερ, έμεινε ανικανοποίητο ως προς την έλευση του πατέρα του, αλλά ίσως αυτές είναι από τις κβαντικές αβεβαιότητες, τις οποίες πρέπει να συνηθίσουμε και στις οποίες θα μας εισάγει σε λίγο ο κύριος Thorne. Η σημερινή εκδήλωση είναι μια συνδιοργάνωση του Πανεπιστημίου, του Συλλόγου Αποφοίτων Αριστοτελείου Πανεπιστημίου Θεσσαλονίκης, των εκδόσεων Ροπή και της Ελληνικής Εταιρείας Σχετικότητας, Βαρύτητας και Κοσμολογίας. Τελεί δε υπό την αιγίδα της Γενικής Γραμματείας Έρευνας και Τεχνολογίας. Παρακαλώ τον κύριο Πρίτανη του Πανεπιστημίου Θεσσαλονίκης, τον καθηγητή Περικλή Μίτκα, να απευθύνει ένα χαιρετισμό.
Κυρίες και κύριοι συνάδελφοι, αγαπητές φοιτήτριες, αγαπητοί φοιτητές, κυρίες και κύριοι, αγαπητέ κύριε καθηγητά Thorne, καλώς ήρθατε σε μια εκδήλωση, θεωρώ εξαιρετική, του Συλλόγου και του Πανεπιστημίου. Ευχαριστούμε τον Σύλλογο και τις εκδόσεις Ροπή, αλλά ευχαριστούμε το Τμήμα Φυσικής που σήμερα νωρίτερα αναγόρευσε τον Κίπ Θόρν, επίτιμο διδάκτορα του τμήματος και του Πανεπιστημίου μας, και μας έδωσε την ευκαιρία να τον έχουμε σήμερα μαζί μας. Ευχαριστούμε βέβαια τον ίδιο τον καθηγητή που αποδέχτηκε την πρόσκληση και την τιμή του Πανεπιστημίου και συγκαταλέγεται πλέον μεταξύ των μελών της μεγάλης και ζεστής οικογένειας του Αριστοτελείου Πανεπιστημίου Θεσσαλονίκης. Σήμερα στον χαιρετισμό μου στην τελετή διάβασα ένα απόσπασμα από δικές του δηλώσεις στο παρελθόν, όπου αναφέρει ότι η αγάπη του για την επιστήμη ξεκίνησε διαβάζοντας βιβλία επιστημονικής φαντασίας, διαβάζοντας Ασίμοφ, Χάινλάιν, Γκάμοφ, όταν ήταν μαθητής στο δημοτικό, στο γυμνάσιο. Είμαι βέβαιος ότι πολλές από εσάς είστε εδώ μέσα από μια παρόμοια διαδικασία. Και εγώ ομολογώ ότι κάπως έτσι αγάπησα την επιστήμη και την διαρκή αναζήτηση της γνώσης. Χαιρόμαστε που είστε μαζί μας. Θα απολαύσουμε όλοι μαζί την διάλεξη και ενδεχομένως αυτό που έκανε τον Κίπ Θόρν να αγαπήσει την επιστήμη μέσα από τα βιβλία του ιδίου, μέσα από την ταινία και τα άλλα που θα έρθουν και περιμένουμε, να οθήσει τη νέα γενιά των παιδιών, των μαθητών που θα ακολουθήσουν ένα παρόμοιο δρόμο. Εύχομαι σε όλες και όλους εσάς, ιδιαίτερα τους φοιτητές μας ή τους επίδοξους φοιτητές μας, να έχουν την δυνατότητα να ακολουθήσουν τέτοιου είδους λαμπρές καριέρες. Και πάλι, Κίπ Θόρν, welcome to Thessaloniki and to Aristotle University of Thessaloniki. It's a pleasure to have you here with us. Θα καλούσα τον κύριο Στεριούλα να παρουσιάσει τον κύριο Thorne και θα σας παρακαλούσα όλους να κλείσετε τα κινητά σας.
Τον ομιλητή θα τον παρουσιάσει ο κύριος Νίκος Στεριούλας, καθηγητής στο τμήμα φυσικής και πρόεδρος της Ελληνικής Εταιρείας Σχετικότητας, Βαρύτητας και Κοσμολογίας. Μόνο μια αναφορά να κάνω. Ο κύριος Κίπ Θόρν ήταν στενός φίλος και του περίφημου Καρλ Σαγκάν και του Στίβ Χόκινγκ, δύο σημαντικές, πάρα πολύ σημαντικές προσωπικότητες της φυσικής, που και εκλαΐκευσαν και επίσης, όπως και ο κύριος Thorne, έβγαλαν την επιστήμη από τα πανεπιστήμια στην κοινωνία. Κύριε Στεριούλα.
Αξιότιμε κύριε Πρίτανη, αξιότιμη κύριε Αντιπριτάνης, αξιότιμη κύριε Κοσμήτορα, κύριε Πρόεδρε, αγαπητοί συνάδελφοι και εκλεκτοί προσκεκλημένοι, αγαπητέ καθηγητή και κύριε Thorne, σήμερα φιλοξενούμε στο Αριστοτέλειο Πανεπιστήμιο Θεσσαλονίκης τον διακεκριμένο επιστήμονα, ομότιμο καθηγητή του Καλτέκ, κύριο Κίπ Θόρν, ο οποίος μόλις αναγορεύτηκε επίτιμος διδάκτορας του τμήματος φυσικής. Είναι μια εξαιρετική τιμή για το τμήμα και για το πανεπιστήμιό μας. Ο Κίπ Θόρν γεννήθηκε το έτος 1940 στην πολιτεία της Γιούτα, στις Ηνωμένες Πολιτείες. Έλαβε το πτυχίο στη φυσική το 1962 από το Καλτέκ και στη συνέχεια έλαβε το διδακτορικό του υπό την επίβλεψη του Τζον Βίλερ από το Πρίνστον το 1965. Έγινε αναπληρωτής καθηγητής στο Καλτέκ σε ηλικία μόλις 28 ετών και 2 χρόνια αργότερα έγινε καθηγητής πρώτης βαθμίδας, ένας από τους νεότερους στην ιστορία αυτού του Ιδρύματος. Και από το 1991 έως τη συνταξιοδότησή του κατήχε την έδρα Φέινμαν στη θεωρητική φυσική και έκτοτε είναι ομότιμος καθηγητής. Ο κύριος Thorne είναι πολύ γνωστός στο ευρύ κοινό για την εκλαΐκευση της σχετικότητας, ιδιαίτερα για την ενασχόλησή του με τις μελανές οπές, τα βαρυτικά κύματα και την πιθανότητα να ταξιδέψει κανείς στο χρόνο ή να μην ταξιδέψει. Εκ μέρους του τομέα αστροφυσικής, αστρονομίας και μηχανικής και της ελληνικής εταιρείας σχετικότητας, βαρύτητας και κοσμολογίας, θέλω να ευχαριστήσω θερμά τους συνδιοργανωτές αυτής της εκδήλωσης για το ευρύ κοινό, τις εκδόσεις Ροπή και το Σύλλογο Αποφοίτων του ΑΠΘ, καθώς και τους χορηγούς, την Επιτροπή Ερευνών του Πανεπιστημίου μας και προσωπικά τον πρόεδρό της και αντιπρίτανη έρευνας καθηγητή κ. Λαόπουλο για την δωρεάν διάθεση της αίθουσας για να πραγματοποιηθεί αυτή η μεγάλη εκδήλωση, καθώς και τη Γενική Γραμματεία Έρευνας και Τεχνολογίας για την οικονομική υποστήριξη. Ένα πολύ μεγάλο ευχαριστώ στους 22 φοιτητές και μεταπτυχιακούς φοιτητές, κυρίως του Τμήματος Φυσικής, που εθελοντικά υποστήριξαν αυτή τη διοργάνωση. Και έτσι, καλώ τον αγαπητό καθηγητή και επίτιμο διδάκτορα πλέον του τμήματός μας, κύριο Κίπ Θόρν, να παρουσιάσει την ομιλία του.
Can you hear me in the back of the auditorium? Good. It has been a great honor today to be awarded an honorary doctorate from this great university. It was an emotional experience, given the importance of this university, the colleagues who work here in my field, and the history of Greece in science, going back to the era of Aristotle. And so I wish to thank the rector and my colleagues and the administration of this great university for this wonderful honor. Could we turn the lights down? Yes, thank you. 1.3 billion years ago, when here on Earth, multicelled life was just forming and spreading around the globe, but in a galaxy far, far away, two black holes were orbiting around each other. What you see here are the shadows of the black holes against a field of stars. We're going to watch them orbit, but it will be a little jerky because the setup we're using doesn't have high enough bandwidth. So pretend it's going more smoothly as it really would. This is what it would have looked like to your eyes if you had been there. And you will see swirling patterns in the stars. The stars are not swirling, just the images because of gravitational lensing. The light from the stars bends around these moving black holes and as it comes to your eyes. And as the black holes traveled around each other, they emitted gravitational waves about which I will speak. They carried off energy, these waves, and the black holes spiraled together and collided in a great cataclysmic collision that generated a strong burst of gravitational waves that traveled out of the galaxy in which those black holes lived into the great reaches of intergalactic space. Across intergalactic space, the waves traveled for 1.3 billion years. And 50,000 years ago, when our ancestors were sharing the earth with the Neanderthals, 50,000 years ago, these bursts of gravitational waves arrived at the outer reaches of our Milky Way galaxy. They traveled onward for 50,000 years until on 14th of September 2015, these waves reached the Earth, touching the Earth initially at the beginning at the Antarctic Peninsula, there down near the South Pole. The waves traveled up through the Earth. They were not influenced, they were not blocked in any way by all of the matter of the Earth. They traveled up through the Earth and they emerged at the LIGO gravitational wave detector, the Laser Interferometer Gravitational Wave Observatory's detector in Livingston, Louisiana, near the city of New Orleans. And 7 milliseconds later, 7/1000ths of a second later, they emerged through the Earth at our second LIGO gravitational wave detector in Hanford, Washington. These waves then stretched and squeezed the arms of these detectors in a manner I shall describe. That signal then went into a light and then into a computer, and we woke up the next morning, those of us working in this project, and saw the results that the computer had produced on an internal web page, and it was wonderful. The strength of this signal was greater than I had expected. It was more perfect than I expected. For 5 months, the LIGO team that had built this detector and a team of scientists from the Virgo project, a European project that was centered primarily in France and in Italy, who are participating in the analysis of our data. They analyzed the data for 5 months to be absolutely sure that this really was a burst of gravitational waves. And these are a photograph of a few of those scientists that are from something like 18 different nations around the world, 1,000 people working on this project. Then on February 11th in 2016, we announced the result to the world, and it became headlines in all of the major newspapers around the world. And it was a marvelous discovery that was shared by all of humanity. So I want to describe how we got here, how this came to be, and then what it lies in the future for gravitational wave astronomy. The story begins with Albert Einstein. Albert Einstein in 1915 formulated a new description of gravity in terms of the warping or curvature or distortion of space and time. That gravity is produced by these distortions of space and time. And then he, about 8 months later, he used the equations from this new description of gravity to predict gravitational waves. And he said what gravitational waves are and that they should exist is when they pass through this room, say, they will stretch and squeeze everything in the room, including you, as they pass through. They, in fact, stretch and squeeze space, and that's stretching and squeezing of space will stretch and squeeze you. And so if we have, in fact, out in interplanetary space above the Earth, we have a large number of particles that are just sitting there with no gravity around to influence them because it's far from all the planets. Then when the waves pass through, you see the stretching and squeezing of these particles because the space in which they are riding is stretched and squeezed. So that was the nature of gravitational waves as Einstein predicted it. But Einstein went on to say in his seminal paper that these waves would be so weak that it was not likely that humans would ever be able to detect them. And that was very, very disappointing to people when they looked at the numbers, the predictions for how strong the waves should be. Nevertheless, in the 1960s, 50 years later, Joseph Weber at the University of Maryland was, in fact, had the courage to start searching for gravitational waves. He designed and built a detector for these waves. And the reason he had this courage was that two things had happened in the intervening half a century. Astrophysicists had identified two types of objects that Einstein never knew about that were far stronger emitters of gravitational waves than anything Einstein had conceived. These are black holes and neutron stars, about which I will speak later. In addition, technology had changed a very large amount, so we now had lasers and computers and many other marvelous pieces of technology, which meant that Joseph Weber could invent a new type of gravitational wave detector that Einstein would not have conceived of based on the new technology that might have a chance of success. Now, I was much influenced by Joseph Weber, but also by my PhD mentor, John Wheeler, who was a theorist at Princeton University. And based on the training I got from Wheeler, and based on ideas that I learned from Joseph Weber, when I arrived at Caltech as a new young professor, I built a research group of theorists who are all working together with me on black holes, neutron stars, and gravitational waves. And one of the things that we did over the next half dozen years was we began to develop a vision for what you could do with gravitational waves if they could truly be detected. And the first version of this vision I laid out together with my student Bill Press in a publication in 1972, a publication titled Gravitational Wave Astronomy. And the foundation for this vision was the enormous differences between the electromagnetic waves with which astronomers have been studying the universe for centuries and the gravitational waves with which we wanted to study the universe. Electromagnetic waves are oscillations of the electric and magnetic fields that travel through space as time passes. Whereas I've described, gravitational waves are distortions of space and time itself, a stretching and squeezing of space. So the physical phenomena are very, very different. Electromagnetic waves in astronomy are almost always what we call incoherent superpositions of emission from individual particles, atoms, or molecules, whereas gravitational waves are emitted coherently by the bulk motions of large amounts of mass or energy, for example, the mass and energy inside the colliding black holes that I told you about. So the mechanisms of emission are radically different between the two types of waves. Electromagnetic waves are all too easily absorbed and scattered by dust and other forms of matter between the source and us, so that astronomers can only see a small portion of the universe. The rest of the universe is blocked out by intervening matter. And by contrast, gravitational waves are never significantly absorbed or scattered. They travel through the Earth without being affected at all. If they were created in the birth of the universe, they would travel out without being absorbed or scattered through the very hot gas of the early universe and come to Earth, bringing us a picture of the early universe. So these three differences in gravitational electromagnetic waves then had implications that seemed quite clear to us in the early 1970s. First, that many sources of gravitational waves would not be seen electromagnetically. They would never be seen with optical telescopes, radio telescopes, gamma ray telescopes. And second, because of all these huge differences, we would be seeing very different things about the universe than you see with electromagnetic telescopes, with light, X-rays, gamma rays, radio waves. And so therefore, huge surprises were quite likely when we finally have gravitational wave astronomy. And therefore, there is a great potential that gravitational waves might revolutionize our understanding of the universe. That was 1972, and in that same year, Ray Weiss, whom I had known when I was at Princeton as a graduate student. He was a postdoc, I was a graduate student. He went to MIT, I went to Caltech. In 1972, he invented an idea for a new kind of gravitational wave detector. He said that you should hang 4 mirrors from overhead supports. You're looking now downward toward the Earth, and so the wires that are hanging, these are pointed out toward you. And when the gravitational waves came by, they would push these mirrors together while they're pushing those mirrors apart at frequencies high compared to 1 hertz, which is the frequency at which a mirror will swing if it's hanging like a pendulum. So this works only at higher frequencies. These mirrors will be pushed together, those will be pushed apart, then these will be pushed together, those will be pushed apart. And he said, let's measure those changing difference in this length of this arm, as he called it, versus that arm, using laser light that goes in, bounces back, it goes through a little hole in this mirror, bounces back and forth many times. The light had been split in 2, and the light goes back and forth in here many times. Then the light comes back together, and it interferes. The light from the 2 arms interfere, and through a process of interference, when the arm lengths change, the intensity of the light rises and falls, as seen by a photodetector down here out of the picture. This process of interference then gave us a gravitational wave interferometer, as Ray Weiss liked to describe it. Now, I saw Ray's idea. I had not yet read his technical paper. We were just within about 2 weeks of submitting for publication a textbook called Gravitation. My thesis advisor, John Wheeler, and I, and Charles Misner. And I thought we really needed to say something about this, but it was obvious to me that this idea was crazy. And so I wrote in our textbook, just before it went to press, and before I had really studied Ray Weiss's idea, I wrote that this is not a promising idea. And nevertheless, I've spent most of my career trying to help Ray make it happen. So why did I change my mind? First, let me tell you why it wasn't promising. The basic issue is numbers. The strength of the gravitational wave is the ratio of the change in separation divided by the separation. We call that the strain, or gravitational wave strain. It's the strength of the waves. That number is 10 to the minus 22. I was guessing for the strongest sources of gravitational waves that might exist in the universe. So already in the 1970s, that was the estimate that we had. And that meant that in 10 to the minus 22, that is, you take 1 divided by a billion and then divide it by a trillion. And that's 10 to the minus 21. And if you multiply that by the length of the arms, 4 kilometers in these interferometers that we ultimately built, you get 10 to the minus 17 meters. Now let me show you how small 10 to the minus 17 meters is. Begin with 1 centimeter, divide by 100, and you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that Ray Weiss said we should use in these gravitational wave interferometers. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, you get the magnitude of these mirror motions. That is approximately 1 trillion times smaller than the wavelength of the light that Ray Weiss proposed to use to measure this. And that just seemed crazy to me. But then over the next several years, I studied Ray's technical paper on this in detail. I had long conversations with Ray, and I had long conversations with Vladimir Braginsky, a superb experimental physicist working on the gravitational wave technology in Moscow, Russia. And from all of this, I ultimately, around the end of 1975, I became convinced that this had a real possibility of success. And so I decided that I would indeed encourage my students to work with me, and that we would devote whatever energy we could to helping, and whatever skills we could, to helping Ray Weiss and his colleagues, his experimentalist colleagues, pull this off, succeed in detecting gravitational waves. In parallel with this, a group at the Max Planck Institute for Astrophysics, and also for quantum optics in Garching, Germany, led by Heinz Billing, had learned about Ray Weiss's idea, and they had built, by 1975, had built and begun to operate a gravitational wave interferometer. And here you see a picture of the spots of light on their mirrors. The spots of light, as the light is making many bounces back and forth on this mirror, and you see the many spots that are produced. Similarly, by 1976, a group led by Ronald Drever and Jim Huff at the University of Glasgow in Scotland had started to build these kinds of gravitational wave interferometers. But Ron Drever had an idea for an improvement on Ray Weiss's design. He said, let's, instead of sending the light through a hole in the mirror and having it bounce back and forth and make many spots, let's coat the mirror so it is very, very reflective, coat it with a reflective coating on all 4 of these mirrors. And then let's make the separation between these mirrors for when the light goes down and comes back be an integer times the wavelength of light. And what that means is that when the light comes in, if a little bit leaks through the mirror into this cavity between those arms, then it will get trapped in here, and the light will go back and forth, trapped between those 2 mirrors many times, and then it will leak out. And so you have just 1 spot on the mirror instead of many spots, and you have a much more versatile experimental setup. But this would be much harder to actually make work in practice. Nevertheless, this looked enough better that it became the preferred design, but just a modification of Ray Weiss's design. I was so impressed by this and a few other inventions by Ronald Drever that I encouraged Caltech to create a gravitational wave experimental group here at Caltech. And after a search for somebody to lead it, Caltech decided to bring Ronald Drever from Glasgow, Scotland, to lead the Caltech effort. And then we brought a man named Stan Whitcomb from the University of Chicago, who was previously doing infrared astronomy. We brought him to Caltech to be an assistant professor helping Drever lead this. And Stan Whitcomb led then the construction of a gravitational wave interferometer that had 40-meter arms. That was 40 meters seems very big, but in fact it is just 1/100th the length of the arms in the ultimate LIGO gravitational wave detectors. In parallel with Caltech doing this, Ray Weiss at MIT was completing a 1.5-meter prototype, but he was also he and his group were carrying out a feasibility study to figure out all the things that might go wrong if you tried to build a huge gravity wave interferometer, something that was several kilometers in size. Based on that feasibility study and the experimental work from the prototypes, the small interferometers at Garking, at Glasgow, at MIT, and at Caltech, MIT and Caltech got together in 1984 to create the LIGO project with the leadership of Ray Weiss, Ron Drever, and me. Now, we were a leadership that was the worst, most incompetent leadership that the physics community has ever seen for a big project. MIT was pushing in one direction, Caltech was pushing in another direction, and we couldn't make decisions rapidly. And so it became very obvious after a few years that we had to get ourselves a single director, a forceful director who would get the two institutions working together in a very effective way and push us forward. And so we brought on Robbie Vogt, who had been the first chief scientist at the Jet Propulsion Laboratory. That's a branch of Caltech that has the interplanetary missions that NASA does. So he'd been their first chief scientist. He had led moderately large projects, but not really large projects, but he had a lot of wisdom. And he then got the two teams working together effectively, and he led us in writing a proposal to construct LIGO, our dream for detecting gravitational waves. And in this proposal that we sent to the National Science Foundation in the United States, we said that we would first build facilities in which these gravity wave interferometers would reside. Then we would have a two-step strategy. We would begin with an initial set of interferometers that would not be good enough to detect gravitational waves probably. If nature was really kind to us, we might see some waves, but probably not. But from the things that we learned with these initial interferometers, the experimental team that I was working with, would then design and build more advanced, much more complex interferometers with much better sensitivity, which would have a high probability of seeing gravitational waves. So this was 1989. Because we were saying we were going to have to do this in two steps, and that's not the way anything has ever been done in astronomy before, we had opposition from a number of very powerful astronomers in the United States. And as a result, it required us 3 years to convince the National Science Foundation and the US Congress to give us the funding to do this. But once we had convinced them, and had told them that it's going to require 2 generations of interferometers, initial and advanced. Once we had convinced them, they backed us completely, both Congress and the National Science Foundation. They backed us whether the Republicans were in control of the government or the Democrats were in control of the government. We were backed completely. We never had major budget cuts as we moved forward toward ultimately detecting gravitational waves. In 1994, we brought on a new director who had much more experience than Robbie Vogt in leading large projects and had really had the skills required to pull this off successfully. That was Barry Barish, who shared the Nobel Prize together with Ray Weiss and me. And he was just the key to making this thing succeed. He one of the things that he did was he built led us in building the facilities, and then he expanded LIGO, expanded our collaboration to include not just Caltech and MIT, but 1,000 scientists and engineers in 80 institutions in 16 nations. This had to be done because detecting these tiny, tiny motions of the mirrors was so difficult. There were so many things that could go wrong that we had to have a very large team to be able to figure out and build apparatus to deal with, counteract all the huge number of things that could go wrong. Then, from 2000 to 2010, under Barry Barish's leadership, we built the first gravitational wave interferometers in LIGO and began the first gravitational wave searches. In about 2006, Barry was stolen away from us by the high energy physics community to lead their design for their next very large particle accelerator. And so we then had a succession of two other very good, very excellent directors who led us, Jay Marks and then David Wrightsey. I just want to highlight the fact that when you have a very big project and it's very complicated, having the right leadership is tremendously important. And typically, a young field like ours doesn't have the right leadership in it at the beginning. So you bring somebody in, typically from high energy physics. That's a physics piece of the physics community that really does have a lot of experience with this. And they pull it off. And that was what we had both with Barry Barish and with Jay Marks. David Wrightsey, our currently director who grew up in our field, is the first director we've had who began in our field. 2010 to 2015, under Jay Marks and then David Wrightsey's leadership, we installed our advanced interferometers. And in November of 2015, we were just getting ready to do our first gravitational wave search. But I have to back off and then say something else was very crucial in order to pull this off in the end. And that was that we understood colliding black holes. Already in 1983, when we were planning LIGO, it seemed clear to me that the first thing that we would see would be collisions of black holes. I thought that was really quite probable. I won't go into the reasons why. But I was concerned that we could not, with pencils and paper, solve Einstein's equations to predict the details of the waves that would be produced when two black holes collide. This could only be done on supercomputers. And so it was essential that we be able to do computer simulations of this. We also had estimates already in 1983 of how strong these waves would be. This was, again, this magic number of 10 to the minus 21. And so that was also guiding us in all of our LIGO work. So the numerical simulations were needed. We call this numerical relativity. And the effort then to do these simulations has actually begun back at about the same time as Ray Weiss and I started working on gravitational waves back in the 1960s. By the early 2000s, I became quite worried. I became quite worried because nobody working on numerical relativity could simulate even one orbital motion of two black holes around each other. The computer would crash before you did more than about a quarter of an orbit. There was something deeply wrong with how this was being done, maybe more than one thing deeply wrong. And so I became quite alarmed, and I left day-to-day involvement in LIGO. So the great success that LIGO had was not really in the end due to me. It was due to the next generation of people, and among them the theorists that I had actually trained. Many of them I'd trained who took over the roles that I was playing. But I went off then to build a collaboration with Cornell University, a group led by Saul Tucholsky, who in my view is the best of all of the numerical relativity experts. And we added Caltech onto his group as sort of an appendage of his group doing these simulations. We joined in, and that then led ultimately in 2005, the first successful simulations of two black holes going around each other and colliding by Franz Pretorius, who was a postdoc in my group at Caltech. And then by 2014, the simulations were mature enough for LIGO's first gravitational wave observations. September 14, 2015. The first gravitational wave search with the advanced interferometers was planned to begin on September 17. The team was tuning these detectors. They're complex detectors. There are many things that you can change and adjust. They're trying to bring them into most optimal configuration for that first gravitational wave search. That night of September 14, the first gravitational wave signal came in and was seen by our 2 gravitational wave detectors. The signal was so strong that when I woke up in the morning and saw the signal, I didn't really believe it could be real. This is what the signal looked like before the signal had been cleaned up. This is basically the raw signal. If I can get technical for a moment, bandpass filtered to remove everything above 300 hertz and everything below 30 hertz because the detectors are particularly noisy up there and down there. But other than that, this is just the raw signal at Livingston, Louisiana, plotting upward the stretching of one of the arms and downward the squeezing of that arm. So there's a stretch, squeeze, stretch, squeeze, stretch, squeeze. The numbers here are in units of 10 to the minus 21. And this was the signal at our other detector in Hanford, Washington. After the signal was cleaned up, we had this gray band of oscillations and then a dying out of the oscillations. And we then took the numerical relativity calculations and searched for a particular pair of black holes in terms of the masses of the black holes and the spins of the black holes, though this was not affected much by how fast they were spinning. So primarily the masses of the black holes and how far away they were. And by adjusting that, how heavy the black holes were and how far away they were, we were able to produce a trace, the red trace, that matches the gray experimental data almost perfectly. And what was the source then? It was 2 black holes that went around each other that had masses of 29 times the mass of the sun and 36 times the mass of the sun. So that's a total of 65 solar masses. The final black hole was 62 solar masses. So it was as though you had taken 3 suns, annihilated them, destroyed them, and turned all of their mass into an enormous burst of gravitational wave energy. This is what had happened. And that 3 solar masses of gravitational wave energy came out and so quickly, in about 1/10 of a second, that the power output, the energy per unit time, was 50 times larger than the power output of all of the stars in the universe put together, but just for 1/10 of a second. But you can regard that then as 50 universe luminosities, the most powerful explosion that humans ever had any evidence of, except for the birth of the universe, the Big Bang in which the universe was born. And no light, no X-rays, no radio waves, only gravitational waves. We wouldn't have known about this without a gravitational wave detector. So this was truly exciting. We carried out 2 gravitational wave searches, improving our detectors in between the searches in the period between September of 2015 and August of 2017. And we saw 10 pairs of colliding black holes. These are simulations of those 10 pairs of colliding black holes. You see some big black holes, some much smaller black holes going around each other and finally colliding and merging. We wanted to know where these collisions were occurring on the sky in order to tell our electromagnetic astronomer friends where to go look for light, X-rays, radio waves, and so forth. And for the first few gravitational wave collisions, we had very poor angular resolution on the sky. So this is an image of the sky. The sky is painted onto a black sphere. And what I'm showing you here in red is our best estimate from the data as to where that first pair of colliding black holes was located. This was very, very bad accuracy for the region in which that first pair of colliding black holes was located. Why so bad? Well, it was pretty narrow in the north-south direction. I told you the signal first arrived in Livingston, Louisiana, and then Hanford, Washington is more or less north of Louisiana, and it arrived there 7 milliseconds later. So we knew then that the source was in the south with moderately good accuracy in the north-south direction. But we did not, I'm sorry, this was the first signal. It was in the south. But we did not know in the east-west direction hardly at all where it was. Then in August of 2018, the advanced Virgo gravitational wave detector, which our colleagues in France, Italy, the Netherlands, Poland, and Hungary had all been working on very vigorously, it went into operation, and we saw a gravitational wave burst that was seen by all 3 detectors, the 2 LIGO detectors and the Virgo detector, And here was the error box as to where it was located on the sky. Very, very small compared to these earlier error boxes because we had 3 detectors. We could localize it in the east-west direction as well as the north-south direction. And so we were off and running now and being able to tell the electromagnetic astronomers where to look. Just a few days after that, we saw gravitational waves from 2 neutron stars orbiting around each other and colliding. These stars each has a diameter of about 20 kilometers, the mass of the sun. In the core, the density of the matter is 10 times the density of an atomic nucleus, tremendously dense when you pack 1.5 solar masses of matter into a region just 20 kilometers across. And as these neutron stars orbited around each other, they emitted gravitational waves and spiraled together. And as they spiraled together, the waves got stronger and stronger. And then the stars collided. They produced a gigantic fireball of hot nuclear matter expanding outward into space and emitting all forms of electromagnetic radiation that there are. That fireball was opaque at first, and so nothing could get out. This is called a kilonova by astrophysicists. But here is the gravitational wave signal in a form that will not explain. And the key point is that 1.7 seconds after the collision as seen on Earth, the first gamma ray burst came out. Gamma rays are the highest energy photons carrying electromagnetic radiation. The highest energy photons, and they were therefore the first ones to come out of this fireball as the fireball became more and more transparent. And the gamma ray burst was in this region on the sky, not very good resolution on the sky. LIGO and Virgo said it was in that region down here, this dark green region. But then a few hours later, X-rays were seen, then ultraviolet, then optical radiation, then infrared and radio waves. And with some of these, you could actually pinpoint the galaxy in which the neutron stars collided, the galaxy that was sitting right down here. This was the beginning of what we call multi-messenger astronomy, where you look with many different wavelengths of electromagnetic waves and with gravitational waves of the same event. And it was a marvelous beginning because, well, first of all, something like 15 or 20% of all of the world's astronomers went and studied this with their kinds of telescopes. So it was the most studied event in the history of astronomy. And it taught us things that we could never have learned in any other way. First, from the gravity waves, we knew it was 2 colliding neutron stars. Then from the electromagnetic waves, it was possible to deduce that huge amounts of gold and platinum were produced by the collisions of these 2 neutron stars. So much that when you then estimate how many neutron stars collide in our universe, you could deduce that most of the gold and platinum in all of the universe is produced when neutron stars collide. This is one of the deductions, one of the first wonderful deductions from multi-messenger astronomy. We began our 3rd gravitational wave search with our LIGO and Virgo gravity wave detectors on April 1st of this year. So that's about 7 weeks ago, with improved detectors. And we now have a smartphone app that has been created by the LIGO Virgo team. It's called Gravitational Wave Events, or GW Events. If you go and you download that app onto your smartphone, then it will come up and it will tell you within minutes of every gravitational wave discovery of what was discovered and where it was located on the sky and how far away it was. Then that was the way that we alert then. The LIGO Virgo team will notify the electromagnetic astronomers, here is where you should go look. We just saw gravitational waves. Go see if there are X-rays or light coming from that same place. So here are lists of events. You can just click on one of these events and see what's inside, see the details of the gravitational waves, and then also of the electromagnetic waves and the neutrino searches that were carried out. It's quite interesting that, well, this is really in the past 12 days, because I made this slide 2 days ago. There were 5 black hole collisions. And you can go in there and look and see what they were. 5 black hole collisions in 12 days. Whereas when we were first seeing gravitational waves in 2015 and 2016, it was about 1 a month, 1 every other month. And so These are things that are coming in because the detectors are better, we understand them better, they're coming in faster and faster. And our second collision of a pair of neutron stars occurred about 4 weeks ago. So the world of gravitational wave astronomers is really often running and doing multi-messenger astronomy together with their electromagnetic colleagues. Let me show you a few photographs of advanced LIGO gravity wave detectors. This is as seen from the sky. You saw this particular photograph already earlier. This is the LIGO detector as seen from an airplane. LIGO detector in Hanford, Washington. Down inside the corner building, there are vacuum tanks inside which the mirrors hang. So there's a mirror hanging inside this tank. There's a mirror hanging inside that tank. The thing that splits the light in two is inside this tank. And Barry Barish, who made this image, has placed a baseball player there, so you can see how big the human is compared to these tanks. It's his form of humor that he places a baseball player there instead of a LIGO scientist. This is a gravitational wave mirror in the LIGO interferometer. It weighs 40 kilograms, and it's hanging by a very thin quartz fiber. It doesn't look like it's hanging. It looks like, like it's being supported, but it's really hanging with all this support mechanism. One of its purposes is if there's an earthquake and that fiber breaks, you don't want this very precious mirror that costs hundreds of thousands of dollars to go crashing to the floor and be damaged. And so that will catch the mirror if there's an earthquake and it falls. These instruments are so complex that there are 100,000 data channels coming out of each of these instruments that carry information. One data channel carries information about the gravitational wave signal, and all the other data channels just carry information about what is going on inside the interferometer and in the environment. Information about all the things that could possibly go wrong. Now, let me tell you just a little bit about some of the technology in these advanced LIGO detectors, just very briefly. Vladimir Brzezinski, that I referred to, my close friend in Moscow, Russia, with whom I had a many decades-long collaboration on, he's an experimenter, I'm a theorist. He told us already in 1968, that's 50 years ago, that however we tried to detect gravitational waves, we would have to measure the motion of heavy masses so accurately that we would see them behave not according to the laws of what we call classical physics, where the location of that object is precisely knowable, but instead according to the laws of quantum physics, where the location of that object wanders randomly in ways that we cannot predict. We call these quantum fluctuations of the position of this object. Now, the object we're talking about in LIGO is a mirror weighing 40 kilograms. And the instrumentation has been designed to measure only the average location of all the atoms in the mirror. We call that the center of mass. So each mirror is, in effect, a particle that weighs 40 kilograms. The random motions, due to this quantum behavior, the quantum mechanical random motions, are at the level of 10 to the minus 19 meters, which is the level of the noise in our advanced LIGO detectors. It is the level at which you start to have problems in seeing the gravitational waves. It's the level of the weakest gravitational waves that we might see today in advanced LIGO. So in advanced LIGO, for the first time, we humans are beginning to see a human-sized object, a 40-kilogram particle, effectively, behave quantum mechanically where it wanders randomly and unpredictably instead of according to the laws of classical physics. And Brzezinski said, you therefore need to develop what I will call, he said, quantum non-demolition technology to deal with this. So this random moving of these particles doesn't get in the way of seeing the gravitational waves. The waves are pushing the particles of the mirrors back and forth by amounts at approximately the same level as these random motions. And so you have to be able to get that gravitational wave signal of the pushing of the mirrors back and forth through this quantum fluctuating particle without the quantum fluctuations demolishing the signal. And so he called this quantum non-demolition technology. And he and his research group in Moscow and my research group at Caltech, my theory group at Caltech, his experimental group in Moscow, collaborated quite tightly from about 1980 up to the present time, and this collaboration is now going on with my group and his group in the hands of younger generations, in devising the basic ideas for the new quantum non-demolition technology. And I'm so proud of my students who really had the key ideas for this. I won't go into the details, but just give you some sense that there really is really interesting new kinds of technology coming out here to underlie LIGO. Let me talk about the future of LIGO and Virgo. There will be huge improvements over the next 2 decades. We will see 10, 20 times farther in the 1930s with something called Cosmic Explorer in the United States, a much larger gravitational wave detector than LIGO. Something called Einstein Telescope in Europe, again, a much larger gravitational wave detector. Seeing 20 times farther means we see a volume of the universe 20 cubed that is 10,000 times greater. And so we will see every black hole collision in the universe with masses of the black holes less than about 200 or 300 solar masses. Every one in the universe, going back to the earliest black holes that formed in the universe. Every one that is arriving in our lifetimes. And we will see lots of other things. There will be big surprises with LIGO and Virgo. What else will we see? We'll see spinning neutron stars. We call these pulsars. We will see black holes tearing neutron stars apart. We'll see the cores of supernova explosions. We'll see things called cosmic strings, which are hypothesized defects in the structure of space, sort of like cracks in a window that can vibrate and emit gravitational waves as they vibrate, that are thought maybe to have been created in the birth of the universe, but nobody's ever seen them. We're searching for the waves from these things, and we will see big surprises. There are 4 different kinds of gravitational wave detectors that will be operating by the 2030s. At gravity wave periods of milliseconds, LIGO and Virgo and other gravitational wave detectors operating on the surface of the Earth will be, as I described, seeing these phenomena I've just been talking about, such as colliding black holes that weigh less than 200 or 300 times the mass of the sun. And these gravity wave detectors operate at frequencies of oscillation of the waves of milliseconds. We will have something called LISA, the Laser Interferometer Space Antenna, which consists of 3 spacecraft that track each other with laser beams with separations of perhaps 5 million kilometers. Separations more than 10 times the distance between the Earth and the Moon. When the gravitational wave comes along, it pushes these spacecraft apart, may push those spacecraft together. You get measurements along 3 arms of the motions of the spacecraft due to the gravitational waves. And with this, which is a European Space Agency mission, we expect to see a number of wonderful things. I'll talk for just a minute or two about some of those things. Well, I guess I have a list here. We will see black holes with masses of 1,000 solar masses to 10 million solar masses. We will, as I will describe, map black holes with exquisite precision. We'll watch perhaps the birth of the electromagnetic force at the beginning of the universe. By a different technique called a pulsar timing array, we will see gravitational waves with periods of years to decades. And we'll see gigantic black holes with masses of 10 million times the mass of the sun, up to 10 billion times the mass of the sun. And then by a different technique called CMB polarization, we will see gravitational waves with periods of hundreds of millions of years, and gravitational waves, in that case, emitted in the birth of the universe. So let me talk in my concluding few minutes about exploring black holes with gravitational waves, and then about exploring the birth of the universe with gravitational waves, and then I will finish. Black holes are made from warped space and time, not from matter like you and me. And so we can visualize the black hole by taking an equatorial surface through the black hole, and that surface will not have a Euclidean geometry. It won't look like the geometry of a flat sheet of paper. Rather, circumferences around the black hole will be much less than diameters. And so in order to visualize this, we imagine embedding that equatorial surface through the black hole in a higher dimensional space, sometimes called the bulk, It's the fifth dimension in the movie Interstellar, for those who saw Interstellar and heard about the fifth dimension in the bulk. You're looking in from the bulk from this higher dimension, and you see the black hole looking like a funnel that goes down. And this is a precise depiction of a fast-spinning black hole, of the warp space around it. Far away, this becomes flat, and that's our universe. Up in here, as you go in farther and farther, circumferences cease to decrease as you go farther and farther in. And so there's a long neck like that. The color coding shows the slowing of time around the black hole. Where it's yellow, time is flowing at 10% of the rate that it does far away. And the white arrows show the dragging of space into whirling motion, a fast motion, a fast angular velocity near the horizon. It's much slower farther away, like the air in a tornado. The horizon down here, where time slows to a halt, is a circle in this diagram because I have removed one dimension. I'm only looking at the equatorial dimension, 2 dimensions of the black hole. When you restore the 3rd dimension, the horizon looks like a flattened sphere. Now, one of the things that Lisa will do is look at the gravitational waves produced when a small black hole orbits around a big black hole. And those gravitational waves, one of my students named Finton Ryan showed in the 1990s, those waves carry a full map of the entire space-time geometry, the geometry of the warping of space and time, of the big black hole that's being explored by the little black hole as the little black hole goes around. And you might ask, how can that possibly be that this little black hole just going around and around produces waves that carry a map of the entire geometry of space of the big black hole? Well, the answer is that the orbit is pretty complicated. For you to see the orbit, that's complicated orbit, I have to remove the warping of space and just show this as though I had an ordinary flat space. I had the big black hole, which is painted purple in here in a simulation by Steve Drasko, who at the time was a postdoc at Caltech. And the orbit of the small black hole. The small black hole has a very complicated orbit. It's complicated because the space-time around the big black hole is so warped. The warping of that space-time makes the orbit complicated. And the small black hole basically explores the entire space around the big black hole as it moves around and ultimately falls into the big black hole. So it samples the entire space, and from it you can build a map of the geometry of the big black hole, map it in the same way as NASA and ESA have mapped the surfaces of Mars, for example. What if the central body is not a black hole? What, for example, if it's a naked singularity? Singularities are places where gravity is so strong that the laws of physics as we know them break down and have to be replaced by a new set of physical laws called the laws of quantum gravity. And singularities are thought to exist only in the birth of the universe and inside black holes. But what if you had a naked singularity that's sitting here in this room or out in space that you could explore as a physicist? It would be wonderful because you could then do experiments to look at the laws of quantum gravity that are controlling the singularity. But if you have a central body that's a singularity, then it turns out, as John Drew Brink, who is a physicist, a woman physicist in South Africa, showed, the orbit of a small black hole going around this singularity is chaotic. This orange orbit is very chaotic in the mathematical sense. So you try to build a map and you have great difficulty, and you conclude you're really looking at gravitational waves that are produced by something going around a naked singularity. Also, what we are doing with this studies of black hole, gravitational relation of black holes, is studying the dynamics of the geometry of space-time when black holes collide. We call this geometrodynamics. And we explore this by computer simulations and then verify the simulations by the gravitational wave observations, that the predictions of the simulations are correct. So this is the prediction of the simulations for how the warped space-time geometry behaved for that first black hole collision that LIGO saw in 2015. You see the two funnels going down here, the color coding showing the slowing of time. We slowed the movie down as the black holes are close to colliding. And this creates, in the shape of space, a gigantic splash, 2 splashes, one on either side of the black hole, as the collision occurs, and the warping of time is oscillating wildly as well. And then this these oscillations die out and the gravitational waves go flying off, carrying 3 solar masses of gravitational wave energy. That is an image of geometrodynamics, the dynamics of the warped space-time in a black hole collision. And we are exploring that with LIGO's observations together with computer simulations. Finally, we will be, over the next several decades, observing the birth of the universe and the birth of the fundamental forces that govern the universe. Let me begin first with the birth of the electromagnetic force. There are 4 fundamental forces according to our knowledge of physics: the electromagnetic force, electricity and magnetism, the gravitational force, strong nuclear force, and weak nuclear force. 4 of them. But when the universe was 10 to the minus 12 seconds old, there was something different. There was an electroweak force, and there was no electricity and magnetism. There was no weak nuclear force. Those 2 kinds of forces were unified into one force that was quite different. And at age of 1/1,000,000,000th of a second, as the universe was expanding and very hot, the prediction is that this electroweak force that previously existed, it comes apart. It came apart, and the electromagnetic force was created, and the weak nuclear force was created. This is called the electroweak phase transition. And this may well have happened inside bubbles. This is called a first-order phase transition. Like the phase transition, that's a technical phrase, for the formation of water droplets out of water vapor. The water droplets, they form as droplets. And here, the region where the forces are separate, so you have electromagnetic forces inside this bubble and inside that bubble, but in the black region, you just have the other kind of force. The electromagnetic force has only begun to come into existence inside these bubbles. And the prediction is that as these bubbles form, they then expand at close to the speed of light. They collide, and the collisions produce great bursts of gravitational waves. And as the universe subsequently expands, the wavelength of these gravitational waves expand until today the wavelength is just right for LISA, the European Space Agency's mission, to see those waves. And so this is really exciting that we have the prospect with LISA to watch the birth of a fundamental force in the first fraction of a second of the life of the universe. Finally, we have the prospect of watching the birth of the universe itself. According to our understanding of the laws of physics, some gravitational waves had to come off of the Big Bang singularity in which the universe was born. Precisely what came off, we aren't sure, but the conventional wisdom is that what came off was the absolute weakest gravitational waves that the laws of nature allow. These are what are called vacuum fluctuations, tiny fluctuations like the fluctuation of the quantum mechanical 40-kilogram quantum mechanical mirror that I talked about. Here it's tiny fluctuations of gravitational waves. That's the conventional wisdom. But whatever came off of the Big Bang is predicted to have been amplified by a very rapid expansion of the universe in the first tiny fraction of a second of the age of the universe, called inflation. Inflationary expansion, which ended when the universe was about 10 to the minus 33 seconds old, we believe, and we have moderately good evidence observational evidence to justify that belief. This inflation then will have amplified whatever came off the Big Bang, even if it's only tiny fluctuations, to form a rich spectrum of gravitational waves. Those gravitational waves are predicted to have traveled outward through the universe at a very special time when the universe was about 380,000 years old. That was the first time that light could start to propagate in the universe, because before that, the universe was so dense and so hot that light was trapped, and it just couldn't travel anywhere. It would get emitted, absorbed. It would scatter off of particles, and so it was trapped. And at that point, when it could first start to travel, it formed what by today we see as something called cosmic microwave radiation or cosmic microwave background. These gravitational waves, at that time when this radiation when the light was first able to propagate, they put a pattern of polarization. This is a technical phrase, a technical thing, polarization on those gravitational waves. And that polarization pattern is something that is a holy grail for experimental physicists to find. and search for that pattern of polarization that carries indirectly the details of the primordial gravitational waves from the Big Bang is underway in a fast and furious manner. The signal has been seen, but there is noise in the observations that the astronomers have to figure out how to remove that noise. When this was ultimately cleaned up and we see the spectrum of the gravitational waves from this measurement process, that spectrum will be a combination of what came off the Big Bang and what inflation did. So we will be observing and learning about the combination of inflation, which we really want to learn about, and the birth of the universe. And we will see also this combination in primordial gravitational waves with a successor mission to LISA, where we will have LISA-type detectors scattered around the orbit of the Earth or going around the sun, looking out to observe all the gravitational wave signals in a particular frequency band that this detector is capable of seeing. See everything, including the primordial gravitational waves from the birth of the universe, but this will probably be around 2050. I turn 110 in 2050. I intend to live to that age 110 in order to see this and see whether or not the predictions that my colleagues are making agree with the observations. And I hope that the observations disagree, because that will be very exciting and it will start to teach us new things about the birth of the universe. So let me conclude saying that it's 400 years ago that Galileo built his first little optical telescope, pointed it at Jupiter, and discovered the 4 largest moons of Jupiter. It's 3 years ago that our LIGO started to operate its advanced LIGO gravitational wave detector and discovered the waves from colliding black holes 1.3 billion years ago. So 3 years ago that was seen. And when you look at and contemplate the enormous changes in our understanding of the universe that have come from electromagnetic astronomy, beginning with Galileo, the enormous changes over the last 400 years, our understanding of the universe is so radically different than in Galileo's time. I invite you to speculate about what changes we will see in our understanding of the universe that come jointly from gravitational waves and electromagnetic waves, from multi-messenger astronomy over the next 400 years. Thank you.
Νομίζω παρακολουθήσαμε μια εξαιρετική ομιλία από τον καθηγητή Thorne. Θα έχουμε τη δυνατότητα, σύμφωνα με το πρόγραμμα, κάποιων ερωτήσεων, 2-3 ερωτήσεων. Αν θέλει κάποιος να ρωτήσει κάτι, νομίζω υπάρχουν μικρόφωνα να δοθούν, ώστε να υπάρχει και μετάφραση της ερώτησης. Λοιπόν, είναι κάποιος που θέλει να κάνει κάποια ερώτηση για το θέμα? Δεν βλέπω, Η κυρία εδώ μπροστά μου. Εδώ.
Can you hear me? Okay, that's fine. Okay. I would like to congratulate you for this beautiful lecture. My question is that you mentioned that we can able to detect gravitational waves from primordial black holes, that they are, I don't know, in the early universe. How can this be possible? Because I'm thinking that gravitational waves travel with a specific velocity. But at the same time, our universe is expanding. So how can we have a maximum distance that we cannot go further we can not detect further gravitational waves? I don't know if I was very clear.
So this is a very interesting question. So
Thank you.
So first, one slight correction. We expect to detect gravitational waves from processes in the birth of the universe, but not primordial black holes, but from this birth of the electromagnetic force, or from these cosmic strings that I talked about, or from the birth of the universe itself. But yes, the universe is expanding, and if the source is so far away that the universe is, that the signal travels slower to us than the expansion of the universe, then we can't see it. What that means is that we have a horizon for our universe beyond which we can't see. And so but everything inside that horizon we can see. But there's the boundary. Another way to talk about the boundary is that things that we see that are at that boundary, at the horizon, we see them as they were at the birth of the universe. And we can't see beyond there. So we can see things that we see that at the birth of the universe, they are coming from our horizon beyond which we can't see. And we can see everything that is closer. We see it as the waves were emitted sometime after the birth of the universe.
Άλλη ερώτηση. Μία θα κάνω. Ορίστε, υπάρχει ερώτηση. Δώστε, αν βλέπετε κάτι, γιατί δεν βλέπω.
Επειδή τα αγγλικά μου δεν είναι πολύ καλά, μήπως θα μπορούσε κάποιος να μεταφράσει μετά. Το ερώτημα είναι, υπήρχαν δύο θεωρίες για το ΣΥΜΠΑΝ παλιότερα.
I'm waiting for a translation. It's on to.
Η μία ήταν η θεωρία σταθερής κατάστασης και η άλλη το Big Bang. Οι ανακαλύψεις που φέρνουν τα βαρυτικά κύματα μας πλησιάζουν ή μας απομακρύνουν. Τα βαρυτικά κύματα επιβεβαιώνουν την θεωρία του Big Bang ή φέρνουν ξανά κάποιες αναμνήσεις από τη θεωρία της σταθερής κατάστασης.
So, Professor Thorne, the question was whether gravitational waves verify the Big Bang cosmology or the steady-state cosmology.
I'm sorry, one more time.
Yeah, so the question was whether gravitational waves, the detection of gravitational waves, verifies the current understanding of Big Bang cosmology or the old model of steady-state cosmology.
So which is the other model?
Steady state.
Oh, steady state. Okay, yes. So you are from my generation, where we looked seriously at the steady state as an alternative to the Big Bang. We share this as part of our shared history. We have much evidence already from in other ways that there was a Big Bang and there was not a steady state. When we do ultimately see gravitational waves from the Big Bang, as I expect we will, that will completely destroy the steady state if it's not already destroyed. These waves will be the ultimate proof of the Big Bang, and the ultimate actually proof in the sense of beginning to observationally understand the Big Bang.
Υπάρχει άλλη ερώτηση? Μπροστά εκεί, σηκώνω δύο χέρια. Έχουμε κάποιο μικρόφωνο εκεί? Δώστε.
Good afternoon. It's an honor for me to make you a question. You said there were of LIGO, one black hole of 36 solar masses and one black hole of 29 solar masses, 1.3 billion light years away, who have merged. How do you know this? Couldn't be one black hole of 12 solar masses and one of 10 in a distance of, let's say, 300 million light years?
So, no. we determine the mass. So we determine the mass of the black hole by the frequencies of the gravitational waves that are emitted. So the total mass is easiest to understand. When the black holes collide, they're going around each other at close to the speed of light. And so the period of those gravitational waves is approximately the light travel time around the size of the black hole. So that gives you the size of the black hole approximately. If you know the size of the black hole, you then know its mass, because there's a direct correlation between size and mass. And so the pattern of the frequency of the gravitational waves as the two black holes go around each other actually carries both masses of the black holes. So we get the masses from the frequencies of oscillation. Then knowing the masses, we know how strong the waves are if you were up close to them. And then we look and we see how strong the waves were seen at Earth, and that tells us how far away the source was. And so, so we see, and this is all done by comparing with the numerical relativity simulations. Simulations, the oscillation rates of oscillation, the simulations carry the information about the masses. And you get these frequencies of oscillations to match the observations, determine the masses, and then you look at the strength of the waves in the simulations compared with what's observed, and you get the distance. Let me just make one further remark. It was Bernard Schutz, a superb relativity theorist, and I'm proud to say another of my former students, who first realized that we could actually determine the distance in this way. And in fact, that just precisely what kind of distance you could determine, something called the luminosity distance. And this then idea that he had in the mid-1980s, long before anybody else had really thought about it, underlies much of the work about exploring the universe in cosmology that is now beginning to be done by observing black holes, the gravitational waves of black holes and neutron stars. And he, I think, was one of the mentors of a number of the young relativity theorists who have been professors here at this university. So I consider them with great pride my grandchildren, because I mentored Bernard Schutz and he mentored them.
Thank you very much, Professor Thorne. Ευχαριστούμε πολύ και για εσάς.